Hello everyone and welcome to All Things Air Quality. In this video I'll explain how to determine stack gas density from stack conditions and its composition as measured on site. Gas density, for which we use the symbol ρ, is defined as mass of a gas per unit of volume. Suppose we have this volume of gas and inside it we have different particles. We have the orange, the blue and the green particles. If the volume of this box is 2, the mass of the blue particles is 1, the mass of the green particles is 2, and the mass of the orange particles 3. The density is equal to 3 of the blue particles plus 2 of the green particles, and we have 2 of the orange particles, and our volume was 2. So therefore, the density is 13 divided by 2, and that will give us 6.5. So this brings us to our original problem. How do we determine density from our stack test? We know that this is not measured directly in a stack test. So in order to determine it from stack test measurements, we make use of the ideal gas law. Now the ideal gas law is normally written in terms of pressure, volume, the amount of gas in moles, and temperature. But it can be rewritten in terms of density. The number of moles in the gas is equal to the mass of that gas divided by the average molar mass of the gas. So big M over here is the molar mass. So we can substitute this relationship into our ideal gas law. That gives us this equation over here, and at least now we have both the mass and the volume over here. That is part of our definition for density. If we reshuffle this equation by taking the molar mass over and we divide by the density to take it over to the other side, we will get this over here. Here we see mass divided by volume, which is our definition of density, and therefore we can substitute it. The resulting equation now has our term density in it. We have the formula for gas density in terms of pressure, which we measure, temperature, that we measure, and molar mass. Now, this molar mass is the average molar mass of a gas. We do not measure it directly, but it is determined from the composition. So that is the next thing we need to do. A stack gas, or even air, consists of different particles. These particles, such as oxygen, nitrogen, and carbon dioxide, each have their own molar mass, which is different. So therefore, if the composition of your gas is changing, the average molecular mass of the gas is changing, and therefore the density of the gas is changing. The average molar mass of a gas is equal to the sum of all the components taken as a fraction of the component times its molar mass for each component. Now this might look or seem complicated if you're not used to this notation. All what it means is, suppose we have a gas that consists of oxygen, nitrogen, water, and carbon dioxide, which is a very typical stack gas. This equation will simply look like this. Because the molar masses are constant and already known, we can already rewrite this equation, which just means we need to know the composition of our gas to get the average molar mass. So from here on, I'm going to explain it with a practical example. In our stack test, we measured oxygen and carbon dioxide with our analyzer, and we got the oxygen as 16% and the CO2 as 5%. You will notice that I've written here with condenser. Most of these analyzers are fitted with some sort of water trap or condenser to first dry the air, and they therefore measure the gas composition without the water or excluding the water that is in the stack gas. The balance is therefore nitrogen. So we know that all the gases together should add up to 100% with the water removed. So therefore, the nitrogen concentration is 100% minus the 16% for the oxygen minus the 5% of the CO2, and that gives us 79% for the nitrogen. Okay, so now we know the dry gas composition. How do we get the water fraction? So for this example, I'm just going to give it to us and say our water concentration is 5% volume per volume as measured with our isokinetic train. There will be a separate video explaining how to do that calculation. This 5% water is 5% of the total gas. So these concentrations over here refer to a dry composition. So if 5% of our total gas is water, then Our dry gas makes up 95% of our total gas. So to convert these concentrations of gas that was measured or determined on a dry basis to actual concentrations, we simply take the concentration measured dry and we multiply it by the fraction of dry gas. So for this example, we have 16% of oxygen and our fraction of dry gas is 95%. And I say that because we had 5% water from our total gas, and if it's 5% water, the remainder must be 95%, which will be our dry gas fraction. And that will give us 15.2%, or we can say that is equal to 0.152 as a fraction. Therefore, we now have XO2 is equal to 0.152. Back to our original problem, we have a fraction of oxygen, 0.152. We still need to determine a fraction of CO2, of water, and of nitrogen. The fraction of water is 0.05 because that's already given to us as a fraction of total gas and not the fraction of a dry gas. The fraction of CO2 is equal to 5% times 0.95 or 95%, and that is equal to 4.75% or 0.075. And now the same for the nitrogen fraction. We have 79% dry nitrogen times 95%, or you can say 0.95, and that will be 75.05% of a total gas, or 0.7505. You can round it up if you want to. Now we have the nitrogen fraction of the total gas, we have the carbon dioxide fraction of the total gas, we have the water fraction of the total gas, and we have the oxygen fraction of the total gas. And now we can calculate the average molar mass by just substituting them. Plug that into our calculator and it will give us 28.9 gram per mole or kilogram per kilomole. Those are equivalent. This is what we need in our ideal gas law to determine the density. Suppose our gas is at a pressure of 100 kilopascal and the temperature is, say, 400 Kelvin. We can now determine the density of our gas. We substitute our pressure of 100, our molar mass as determined on the previous slide of 28.9. This is our gas constant of 8.314 and our temperature of 400 Kelvin. We can plug all that into a calculator and that will give us a density of 0.87 kilogram per cubic meter at the conditions of 100 kilopascal and 400 Kelvin. This is for gas. We used our gas analyzer and we measured oxygen 16% and CO2 5%, dry basis because our analyzer is fitted with a condenser. From there we determined that the balance of the dry gas must be 79% nitrogen. We knew from our isokinetic test that the water fraction or the moisture content of gas was 5%, and therefore this dry fraction of gas was only 95% of the gas. We therefore corrected our dry gas measurements to be fractions of our total gas. And there you have it. I do have a spreadsheet available that I can share with you to do this calculation. Just let me know in the comments. And also please leave any questions or queries that you might have and I'll see if I can help you.